This is section 2.6, problem number 23. So in this problem, we have the following story. A winch at the top of a 12-meter building pulls this pipe, which is the same length to this vertical position as shown in this figure. So this pipe is pulled towards this direction at this rate, negative 0.2 meter per second, the negative sign, because this distance is shrinking, it's getting smaller and smaller. And this pipe, the distance, the length is a fixed number, 12 meters, okay? So here, I'm gonna draw this diagram. This is the pipe, which is, I call it Z. So this length is fixed. And this type, the x coordinates label it x, and the y coordinates label y. Please note that this distance is the same as this distance. That's why I label this as x. And this building, the height is 12 meters because it's the same length as the pipe, right? So 12 meters. If I label this y, which I will, then this will be 12 minus y, the left over after this 12 meters, right? And this is, I label it as, so what's given is ds dt is equal to negative 0.2, not negative 2. So it's going to be negative 0.2, okay? And then, so we want the dy dt, that's find the rate of vertical change, that at this moment, this tip, the y, the vertical direction, the height is y. So we do want the dy dt. And also its x position is x, so dx dt, when y is equal to 6. Now let's take a look at when y is equal to 6. When this y is equal to 6, we can use this triangle to find the x value, right? To find the x value, this is what I'm gonna do. And so when y is 6, by this x square plus y square equals this z square, and the z is 12. So 12, I plug in 12 here, so this is what we know. X squared plus y squared equals 144. And when y is equal to 6, so plug in 6 here, x squared plus 36 is equal to 144. You can find the x easily. So x turns out to be 6 square root of 3. And another shortcut, okay? If you recognize when you have a triangle, if this is 6, this is 12, the ratio is like the ratio, this is twice of this. Then the ratio of these three sides will be 1, 2 square root of 3. This is actually a 30, 60, 90 degree triangle if you recognize that pattern. Otherwise, you can use Pythagorean theorem. Another thing that we want to find from this relationship is to find the dx, the relationship among the dy dt and dx dt. So here, this is what we're gonna establish next. So look at this one, right? Let's differentiate with respect to t, both sides. So therefore, using the chain rule, the derivative of x squared will be 2x dx dt. Derivative of y squared will be 2y dy dt. Z, which is a constant, so the derivative of z squared is 144, which is a constant. Derivative of constant is 0. And then after that, you definitely can cancel the 2, right? Divided by both sides by 2 to get rid of the 2. And then let's look at, solve for this guy, solve for dy dt. So subtract x dx dt. So this is what you're going to have. And divide both sides by y. So therefore, dy dt is equal to negative x over y dx dt. What that means is, if you find the dx dt, then you can use this relationship to find the dy dt. So now we've established this relationship right there, okay? And then now next, we are gonna look at the, let's make this more concrete here. When y is equal to 6, we already found that x is equal to 6 square root of 3. Therefore, let's plug in here. dy dt will be negative. X is going to be 6 root 3 over 6 root 3. Y is 6 dx dt. So I just plug that in here, right? And then cancel the 6. Therefore, this actually is what we are going to use. Okay. Now, time for us to look at the upper triangle. Because we are given the dx dt, we have not used that condition yet. We will need to use that. So now I'm gonna look, this is the upper triangle. I just redraw the upper triangle here, okay? And the upper triangle, this side is 12 minus y, this side is x. So this is 12 minus y, this is x. When y is equal to 6, right? When y is equal to 6, this 12 minus y is also, equals 12 minus 6, which is 6. So 12 minus the 6 is 6. And x is definitely, at that moment, 6 root 3. We already found that up here. So using this triangle, we can now find what exactly s, the length of s, the distance of s, when y is 6 and x is 6 times root 3. So this is the relationship we use. This is another Pythagorean theorem. So s squared is equal to this x squared plus this square, right? So s squared is equal to x squared plus 12 minus y squared. And we do know at that moment x is 6 root 3. And then 12 minus the 6 is 6. So 6 squared, it turns out to be 144. And s is 12. So at that moment, s is actually 12. Now, time for us to differentiate this equation with respect to with respect to time t. So the derivative of s squared using the chain rule, 2s dx dt. Derivative of x squared will be 2x dx dt. Derivative of this guy, chain rule again, 2 times 12 minus y times the derivative of the inner function, which is negative dy dt, right? So now, by the way, because every term has a 2, we can divide both sides by 2 to get rid of these 2. So now we have s dx dt equals x dx dt, 12 minus y times. Okay, now this is what's happening. If you remember earlier, we established this relationship, right? So dy dt, you want to replace the dy dt using the negative root 3 dx dt. Here's the reason. We don't know dx dt, we don't know dy dt, so we cannot have two unknowns. That's why we have to substitute this dy dt, rewrite it in terms of dx dt, so that unknown is only one, then we can solve it. So when you plug in negative root 3 dx dt, so we plug in that. There's a negative sign, therefore these two becomes positive sign, right? So we don't need to worry about the sign anymore, it's going to be positive. So now time for us to plug in the values. S, we just found it earlier, 12, so 12. dx dt is negative 0.2, so it's given. And x is 6 root 3, dx dt is what we are trying to find. When y is 6, 12 minus y is 6, and this is root 3 dx dt. So now you just need to solve for dx dt using this equation. I think you can do the algebra. Now, once you find the dx dt, so once you get it, then how do you find the dy dt? That's where you can find the dy dt. So this is the hint for this particular problem.